Hello students, welcome back. Previously we completed section 2. Well, almost as a matter of fact. The one thing we left out is the proof of the law of sines. Yes, we'll do that, but that'll have to wait. We're going to do it at the end of this lesson as an optional video because it's a bit too theoretical. The same goes for law of cosines. The proof is postponed. For now, let us focus upon the application. How to utilize this? Well, we begin with the same kind of convention as before. Triangle A, B, and C. With capital A, B, and C represent the vertices and the internal angles. And then the lowercase a, b, and c are the lengths of the opposite side. And then also pay attention to the color coding. Capital A and then lowercase a, capital B and lowercase b, capital C and lowercase c. They're opposite of each other. Based upon this convention, the relation we get is, well, these three identities, which corresponds to the three angles. One for angle capital A, and then one for angle capital B, and one for angle capital C. Now, in each of these identities, if I remove this cosine part, what do you see? A squared equals to B squared plus C squared. It looks exactly like Pythagorean theorem. Remember? Yes, indeed. If we set the angle A as 90 degrees, then cosine of 90 degrees is 0. 0 times anything is 0, so this entire part is 0, so that part just drops out, and what's left is a Pythagorean theorem. The same goes for angle B and angle C as well. So whatever angle is 90 degrees, if it is, then we end up with the Pythagorean theorem. In general, of course, we have the cosine angles. So you can regard the law of cosines as a generalization of Pythagorean theorem, except that this works for arbitrary triangles, not just right triangle. The case of right triangle is a special case when an angle is 90 degrees, so cosine is 0, so this part just drops out. Now we have these three identities, one for each angle, and we can do some algebraic manipulations and you can solve for the angle A, B, and C like this. Solve for cosine of A, solve for cosine of B, and solve for cosine of C. And then eventually take the inverse cosine. What do you get? The angle formula. From three sides, we can find out the angle through these three. Now, if you prefer to work these out algebraically, like me, then you don't have to memorize all these. You see, we have 9 formulas to remember. That's hard to follow. So clever students don't usually do that. Just take one here, and then the other two obtained by relabeling this, so no problem. And from here, you just deduce the other two. So how do you do that? Well, solve it algebraically. So subtract b squared minus c squared away. Sorry, the typo should be b squared. Alright. And then divide by negative 2bc. Now, let's simplify a little bit. Too many negatives, so multiply negative 1 to both numerator and denominator and change all the signs. The denominator becomes positive. The numerator, positive becomes negative, negative becomes positive. So a squared becomes negative, the others become positive. The end result is this formula here. So deducing this from the original identity is not difficult. And once you get here, then take the inverse cosine and you get the angle formula. You can do the same thing for the others as well. But if you don't feel comfortable with these kind of manipulation, if you choose to prepare all 9 formulas here in your formula sheet and just utilize, well, that's acceptable. I do not really recommend it because there's so many things to follow like that, but if you chose that way, then go ahead, make sure they are accurately written, and you know how to bring those out. Now, we're going to prove this later because it's a bit too theoretical. Instead, let's go ahead to some example problems associated to these. First, solving a triangle. Solve a triangle ABC where A is 5, B is 8, and C is 12. So this is SSS triangle case. We have 3 sides, and that identifies a triangle, right? What are the 3 conditions for congruence? SSS, all 3 sides, and then SAS, 2 sides and an angle between, and then what? ASA? Yeah, 2 angles and a side in between. ASA case was discussed already from the law of sines. We consider the other 2 here, SSS here, and then for SSS, well, one way to handle is to do this. Put the numbers in and take the inverse cosine. Easy. Yeah, okay. Let's do that. Put the numbers in and then do your computation. Inverse cosine of this quantity and punch your calculator. Make sure your calculator is in degree setting. You're going to get about 17.6 degrees like this. Working out the other angles, the same. We have these 3 identities here, right? One for A, one for B, one for C, I mean the capitals. And then cosine of A, cosine of B, cosine of C, like those. And then take the inverse cosine of those. If you do that, you'll get this for the angle B, and you're going to get this for the angle C. It's just a calculator work. Alright, we got all the angles, and all 3 sides. We began with all 3 sides, so we solved the triangle. But let's check, do these angles really add up to 180 degrees? And yes, they do. As a matter of fact, here, by Mathematicus calculation, I'm taking a lot more decimal digits than a default 4 here, so that I get far more accurate answer in the end. In practice, you're going to be off for a little bit, but that's going to be coming from the rounding, so you don't have to pay that much attention to it. One way, of course, is to find 2 angles, and the third one, you obtain it by subtracting previous angle for 180 degrees, but I do not recommend it. My recommendation is to repeat this process 3 times and then check whether they add up to 180 degrees. If they don't, that means you punched something wrong, so you can find out your mistake that way a little bit more effectively. Alright, we went through an example problem of SSS. Now let's go to SAS. We have an angle here, capital A, and 2 adjacent sides, small b and small c. So how do we handle this? Well, using the law of cosines, the first identity will help me identify small a, lowercase a. Alright, the law of cosines, and then we want a, so take the square root, put the numbers in, and run your calculation. Or if you prefer, put the numbers in and do your computation, and then take the square root of that. Either way, it'll work. And what did I get? In this case, about 13.2 units, and that's my small a. Now, how do I find the other angles? Well, we already know how to find angles. We have 3 sides. From the previous example, small a, small b, and small c, with those SSS, we can always find any angle. And yeah, that's what we're going to do. So using the SSS method, we can find angle B by inverse cosine of this, put those numbers in, we get about 35.26 degrees, approximately speaking. And then angle C, again, put the numbers in and do your computation. Same as part A of the problem, the SSS problem. So in ASA problem, find out the third side, and then the other angles using SSS technique. Now we have these three angles. One originally from the problem, and then we found out the other two. Now, do they add up to 180 degrees? You can check. Alright, so much for solving triangles. Now, do you have enough time for applications here? Nice picture. Okay, nice picture. Nice picture. Yeah, they look interesting, but I'd rather do these kind of problems in a separate video. Instead, let's go to the next example. Heron's formula. The area of a triangle ABC can be calculated as follows. And here, small s here is half of the perimeter. A plus B plus C over 2. And then here is the formula, Heron's formula. Square root of s, s minus a, s minus b, s minus c. And as for the proof, we'll probably end up skipping it, I think. I mean, the proof is here, but even for optional video, it's too darn long. Whew, is it really worthy? So I'll probably end up skipping it altogether, unless I have some time to burn at the end of all those proofs of law of sine, law of cosine, and rule of cosines. Well, in this video, let's talk about how to utilize this formula in an application problem. Find the area of the following lot, and then we have three sides. 315, 125, and 280. The computation, all you have to do is put this into this formula. Add them all up and get perimeter and divide by 2. That's going to be your S value. So what is your S? 315 plus 280 plus 155 over 2. And if you do that, you're going to get 360. Alright, 360 is your S value. And square root of 360 here, 360 minus 315, 360 minus 280, do your computation. And then in the end, take the square root. Let's see, did I do that computation here? Yeah, I guess so. Heron's formula is up there. Okay, let's take a little bit smaller font. Alright, Heron's formula is up there. And then S computation, 360, and then put everything to this and run your computation. What do you guess? 17,551.6 square feet. Okay, that was an application of Heron's formula. So, other than this application and the rule of cosines, again, I'm going to cover only in an optional video. Other than those, we are done. Alright, in the next video, we'll talk about these application problems. And then after that, if I have some time to burn, rule of cosines. And then after that, in a still separate video, I'm going to prove the law of sine and law of cosines.